SwayamPrabha. Digital India. Educated India.
Welcome back to another lecture on control systems, and hopefully in this lecture we shall try to wrap up all the loose ends or whatever is remaining of Bode plot thus far that we haven't covered. So in the previous lectures we have seen how to draw a Bode plot, we have seen those different performance metrics specified in terms of frequency domain parameters, and also we have seen the explanation behind certain terms like bandwidth, resonant peak, non-minimum phase transfer functions, so on and so forth. We hopefully now have a better understanding of why those names came into being, right, and what the interpretation is. Also we have in the process of seeing this non-minimum phase transfer function and understanding why it's called so, we have also seen how Bode plots can be used, or at least discussed briefly as to how Bode plots can be used to identify a system transfer function based on our observation of a particular magnitude plot and a phase plot that may be given to us, right. And towards the end of the last lecture we discussed about this thing called bandwidth, which we hopefully justified and reasonably explained was related to rise time, right. So the higher the bandwidth, the better is the system's response, in the sense that it is faster, right. So higher bandwidth is desirable from that perspective, but we saw also that raising this value of gain k, yeah, does not really help us in getting a better bandwidth in the closed loop system, right. So basically this folklore we have kind of justified, albeit not very rigorously, that the open loop bandwidth and the closed loop bandwidth of a transfer function are more or less the same if the loop gain is high enough. Okay. So today we shall try to answer the question of stability. Remember we have discussed how to find out this Kp, Kv and Ka from Bode plot. So everything has been sort of covered, right, everything we wanted to cover in so far as our understanding of controller design goes, yeah, we have more or less covered, but now we want to understand, like, okay, if we design a controller or if we have a system, for example, whose performance we want to analyze, it is not just sufficient to have good performance, yeah, but also we should have stability in the first place, yeah. So for understanding the stability, and more importantly I would say robust stability in this case, and why I am using the term robust will probably be clear by the end of this lecture. So what we are saying is that there are these two terms called gain margin and phase margin, which give us an idea not just about stability but about robust stability, and in that sense I would say this understanding of stability is a little more strongly founded in the roots of control theory, right, than the understanding of stability that we had, which is like if it is in the left half it is stable, if it is in the right half it is stable. This gain margin and phase margin allows us to analyze relative stability in some sense, okay. So you could be given two transfer functions, and knowledge of gain margin and phase margin would allow you to say which is relatively more stable, in the sense that if you perturb a system's parameters, yeah, one of those systems is going to lose stability before the other. So one of them is able to withstand more perturbation before it loses stability. It will turn out that precisely the system with a higher gain margin and phase margin will be the one to be more robust to perturbations, okay. Of course we will not launch into a detailed discussion on robust control, that will take us again too far afield, But hopefully by the end of this lecture you will be able to appreciate why we are making all of these claims, even if they are not made in a very rigorous fashion. Okay. So let us quickly try and understand what this gain margin and phase margin is all about. So we start as usual with a typical magnitude plot of a low pass system, which is what we have claimed our control system is in general, yeah, by virtue of having more number of poles than zeros, right. So let us say, suppose you have, this is the frequency axis, yeah. So let us say this is 20 log m omega and this is phi omega. So we draw it side by side here. So let us say this is the 0 dB line, okay. This is some value here. So let us say your system's low frequency asymptote is like this, then there is a drop, then there is something like this, then there is a drop, then there is something like this. So we are only drawing the asymptotic plots, we are not really bothered about sketching all of this correction, making all of these fine corrections around the corner frequencies and stuff like that, okay. So then we have this. So now, just like we have this bandwidth, which is the intersection of this magnitude plot with the minus 3 dB line, similarly also we have this intersection of this 0 dB line with our magnitude plot. This is what we call as the, this frequency is what we call as the gain crossover frequency. So that is omega GCF. So this is gain crossover frequency. I will explain why these are critical junctures. Again we will have to resort to that understanding of this angle criteria, which we had discussed while talking about root loci, okay. So for example, now you have a phase plot, yeah. So let us say you have starting from 0 and then over here at this is a corner frequency, 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 okay. Fine. So now that we have all of this, so of course there is going to be a dip here, then there is again going to be a rise here, yeah, going to be a dip here, there is going to be a rise here, yeah, then there is again going to be a dip here, yeah, maybe a bigger dip, I do not know, maybe this is 40 dB per decade. So maybe this is a 180 degree dip here, yeah, maybe it is a complex conjugate pole and 0, yeah. So this is a dip here, and then again there is probably an equal rise, right. So again a complex conjugate 0, right. This is all I am making up as I am going, and then again something like this, okay. So of course if you want a finer plot, you can always make this sort of a correction, okay, yeah. Yeah. So this could be a typical phase plot. The exact phase plot could be something like this blue line that I have drawn here. So, or let me make it even worse. Actually, I want, so let us say it goes off like this from here. Yeah. So there is this additional dip here again, let us say. This is 40 dB per decade and it goes off like this and then it goes off like this, yeah. So that is at 60 dB per decade. So then this will not flatten out here, this will continue here, and at this point it will have a further dip. So let me just erase this bit here. So you will have maybe something that goes off until this point, which is here. And then you have a further dip here, okay. You have a further dip here of another 90 degrees. So basically then this blue line will not rest easy, yeah. So this blue line will continue going like this and then it would probably settle down something like this, yeah. So now what I am saying is I am going to draw this minus 180 degree line here, yeah, and I am going to look at its intersection with this. So, suppose this minus 180 degree line intersects here, and this I am going to call as, of course this drawing looks horrible because the lines are not even parallel. So, let me improve upon that a bit, yeah. So, if you would, this is basically it, yeah. So, this is probably where this intersects, right. So, where it intersects with this minus 180 degree line is what we call omega PCF, yeah. So, this is what we call as the phase crossover frequency, okay, phase crossover frequency. And let me just warn you, at this juncture we will be only talking about systems that are stable to start with, as we have done so far throughout our Bode plot, right. So, let us think of a typical system that has all its poles on the left half plane. Let us resort to something we understand well, such as, let us say, root locus, okay. So, this is R, this is JR, this is let us say a pole 0 map as we generally draw for a root locus, yeah, something like this, right. So, we know that there is this asymptote, so maybe it goes like this, yeah, something like this, and well, I do not know, maybe we have another pair of poles here, yeah. So, suppose the centroid is such that these two fellows cross over like this. I mean, I am just sketching it, I am not taking any numerical values, all right. So, suppose at some point, yeah, because the 0 is let us say too far to the left, yeah. So, therefore, the centroid, yeah, the asymptote along which they go to 90 degrees and 270 degrees is on the right half plane. So, there is some point at which they cross over. It could not be, I mean, maybe if the 0 is not too far to the left, if the 0 is close enough, then maybe they would just go about, and for no value of k would you have a crossover from the left half plane to the right half plane. But in general, let us say in this particular case, the way we have chosen the 0 here, that there is one branch of the root locus that kind of goes over to, or maybe, okay, no, in this case actually it will always go over, right, because the number of difference between the pole and the 0 is actually 3, yeah, that is right. So, it will actually always go, right, this asymptote direction I have drawn it incorrectly, I am sorry about that. So, this is basically 4 poles and 1 0, right. So, therefore, the number of difference, the difference between the pole and 0 is 3. So, therefore, of course, the asymptote is going to be something like this. So, it is always going to cross over. But the important thing is, yeah, sorry about that. So, the important thing is, maybe it is rather badly drawn, let me be a little more careful about this, yeah, yeah. But the important thing is that for low values of k, yeah, you notice that for low values of k, yeah, these branches will always be on the left half plane, but this branch, if you are making k very small, it will, at least the closed loop poles will be on the left half plane. Only beyond a certain value of k, so this is say omega oscillation at k is equal to k crit, yeah. So, at k crit is where this crossover happens, right, that is the closed loop pole migrates to the right half plane. So, if you keep your gain very low, yeah, then you will be stable, and this is our understanding of the system, as we have seen earlier also, that that is why we saw that it is not a very smart idea to always use very high values of k, even if it might be desirable from the point of view of reducing the steady state error, because it might even eventually violate stability, right, especially for higher order systems like these. Some asymptotes will always point you out towards the right half plane. So, at some value of k, beyond that value of k, you will always go to the right half plane, right. So, now we want to capture this notion using our Bode plots as well, right. So, let us try and understand what this is saying here. We have this g of j omega, which is basically n of j omega upon d of j omega, right. So, we saw that we pull out some k constant here, and this n of j omega is like 1 plus j omega upon z1 dot 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 till 1 plus j omega upon zm. There are m zeros, and this is 1 plus j omega upon p1 dot 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 till 1 plus j omega upon pn if there are n poles, right. So, this is how we generally cast the transfer function before applying our ideas of Bode plot, fair enough. Now, having put it in this form, what are we going to now try and observe here? We are going to try and observe what this phase margin and gain margin is actually equivalent to. You see, whenever we want to say if this system is closed loop stable or what are the closed loop poles, we have to equate it to 1 plus g j omega is equal to 0. Yeah. So, if there exists some real, or rather let me put it k here, yeah. So, okay, let me just say this is k here. How do I put it here? So, this is, let us say, this part I call as the g tilde, yeah, this part let me call as g tilde j omega. So, this is g tilde times k, yeah, fair enough, right. So, if there exists some real omega such that 1 plus k g tilde j omega is equal to 0, then I am in trouble. Why do I say that? Yeah, then it means that there is some purely imaginary root. Yeah, the closed loop system for the particular value of k that I have chosen, yeah, this k is, let us say, it contains the DC gain of the system as well as the controller incorporated within. So, I have clubbed them together, so lumped them together into this k, okay. So, let us say this is this kp, yeah, there is this kp that I have already applied to this control, to this plant here. So, this is g, this is kp, and this is the closed loop configuration that I am talking about, right. So, this is the system that I have in mind. Now, if this is the system that I have in mind where this kp is there and this the system's DC gain and this kp are being clubbed together, as I said, in this k, alright. Now, if this for some particular values of kp, yeah, if this is equal to 0, it means, and for some real omega, if this is equal to 0, yeah, it means that j omega is a root, and if j omega is a root, it means j omega is a closed loop pole. If j omega is a closed loop pole, then the system has closed loop poles on the imaginary axis, which would result in oscillatory response. And because it has a root on the imaginary axis, I know that if I increase the gain k ever so slightly, because remember from my understanding of root locus, I know that as I keep increasing k, systems branches, the root locus branches have a tendency to go to the right half plane, because initially if the system is stable, they are all in the left half plane, then they gradually start moving towards the right half plane. At some value of k, if there is an omega such that this has a root, then it means that at that particular value of k, I have already reached the imaginary axis. In other words, my closed loop poles, some of my closed loop poles are already purely imaginary. So, that is the restriction on my k. If I apply the Routh-Hurwitz criteria, I will figure out that that is exactly the critical value of k, yeah, beyond which the system will go unstable. Yeah. Now, you might wonder what has all this got to do with this Bode plot, but remember that already when we are writing this in g j omega, this form, this has a very nice Bode plot interpretation. So, basically what we are saying is that the way we have evaluated this critical k using Routh array. Now we can do the same using this Bode plot. Why? Here is the explanation. Consider the value of Kp at which 1 plus kg j omega is equal to 0 has a solution with some real omega, yeah, then that value of Kp is the upper bound on the gain, right, and this is called the gain margin. Okay. So, that means that is how far I can raise the gain and no further. If I keep increasing the gain beyond that, it will migrate to the right half plane. I know from my understanding of root locus that it starts all in the left half plane if the poles are all on the left half plane, and then at some point there is some value of k at which there are purely imaginary closed loop poles. So, beyond that value of k, if I keep increasing further, the poles will migrate to the right half plane. Yeah, that's going to be that's essentially going to be the problem. Of course, you might say there are some pathological cases like we have already discussed some here. So, for example, sometime we have this let us say some sort of a pole 0 configuration like this, where you have one crossover here and another crossover here, and you have one crossover here and another crossover here. Yeah, we have seen this in root locus, no, we have seen something like this, right. I believe this was what that particular root locus looked like, if I am not mistaken, right. Yeah. So, in this particular root locus case, you might recall that there are actually two values of gain k at which there is a crossover. Once it is taking you from the left half to the right half plane, once it is taking you back from the right half to the left half plane. Now, of course, these are pathological cases, but let's not worry too much about this case for the time being. Let us just understand gain margin as people commonly understand it. Okay, later on we will revisit this and we will explain. So, now let us cast our attention back here. Yeah, what happens to this system's magnitude function if you increase k? Yeah, so if from root locus we have seen that if we increase k, the closed loop poles migrate to the right. That is one understanding. But from the Bode plot, if you increase Kp, you see this overall k will increase. Of course, the DC gain part is the component of the system that remains constant. Yeah, but this Kp, if this Kp increases, then this overall k increases. So, if this overall k increases, this open loop Bode plot, this gain increases. If this open loop Bode plot gain increases, we know that this will be lifted up. Yeah, and if this will be lifted up, what will happen to this gain crossover frequency? See, this gain crossover frequency, just like the bandwidth, the gain crossover frequency moves to the right. Yeah. So, this is all as Kp is increased. Yeah, this Bode plot is lifted up, the magnitude plot is lifted up. Of course, it has no impact on the phase plot whatsoever. Yeah, and the gain crossover frequency moves to the right. Now, what happens if this gain crossover frequency and the phase crossover frequency coalesce? Yeah, that is a big problem. That is precisely the situation when, that is precisely the situation when you will have this condition, right, that this phase condition and the gain condition will both be met. See, what does it mean to say that? If omega GCF is equal to omega PCF, is equal to some omega, say, then what do we know about omega GCF? What happens at omega GCF by our definition here? At omega GCF, the gain is 0 dB. So, therefore, we know that G of j omega GCF, this magnitude is equal to unity. And what happens at phase crossover frequency? My goodness, at phase crossover frequency I find that this is 180 degrees. But what is this identical to? And at G j omega PCF, yeah, the angle is equal to 180 degrees, minus 180 degrees if you like, it is the same. But notice now if both omega GCF and omega PCF are equal to some omega in turn, then do I not already have that particular omega? Yeah, I have that particular omega such that 1 plus k g j omega, so maybe I should write g tilde here. So I then have this condition that we have purely imaginary roots of this equation 1 plus k g tilde j omega is equal to 0. In other words, this phase crossover and gain crossover coalescing or coinciding is exactly the situation I want to avoid, because at that condition, yeah, I have this understanding that the closed loop system's poles will be on the imaginary axis, and that is the critical point for stability. So therefore, what we then say is that at omega PCF, evaluate mod of G j omega PCF. Yeah. So you see here, for example, in this instance, yeah, at omega GCF, because the PCF in this case we have seen that omega GCF is less than omega PCF, and we will later see, we will establish that this is actually the condition for stability in general. Of course, there are cases, as I said, there are pathological cases such as this where there are multiple crossovers. We will get to that shortly, I promise. But now look at this. What happens? What does this tell you? If you cast your attention back to this figure here, if you think of what the value of, okay, so let me point that out here. This is omega GCF and this is omega PCF. This is where what happens, yeah. So at omega PCF, if you try to find out this gain, you see that by virtue of the fact that omega GCF is less than omega PCF, this is going to be some negative quantity, no? This is going to be negative. So in other words, this is going to be less than 1. Yeah? And why am I saying this is a desirable condition? Why I am saying this is a desirable condition? It is because this means that when this angle criteria is met, yeah, I do not have the gain that is required to satisfy this condition, satisfy this equation. Okay, right? Now look at this. So if I have seen this, so let me say, let me write this a little more organized way. Now suppose this G of j omega PCF is less than 1, yeah, that is what we are now trying to study. So the question is, what does this imply? Yeah. So I am claiming, I am putting it to you that this fact that omega GCF is less than 1, yeah, it means that I can still, think of this, I can still raise this, I can still give a higher value of Kp until this gain crossover frequency and phase crossover frequency coincide. Look, if I keep reducing this, if I keep reducing this Kp, this magnitude plot is only going to come down and the GCF is going to move further to the left, and the GCF and PCF are always going to stay further and further away. So there is no chance of me satisfying both these conditions simultaneously. The only way I am going to be able to push this to the brink of instability is if I keep raising the value of gain Kp, and that is also consistent with our understanding of root locus, the way we have seen this here. So now what I am saying is that suppose I keep increasing the value of Kp, the fact that at omega PCF at the phase crossover frequency the magnitude is less than unity tells me that I can still keep giving higher and higher gain to my system until it reaches the brink of instability, and therefore I have some positive gain budget. That is exactly my gain margin. So what is the gain margin? If you do not go for the logarithmic expression, so the gain margin is given by 1 by g of j omega PCF. So remember, the gain margin is evaluated at the phase crossover frequency. Yeah. So this is what it is. Okay. So I have this much gain budget. I can still keep increasing my gain until my closed loop poles start migrating to the right. So this gain margin gives me how much gain can still be increased. In that sense, it is a measure of robustness. Yeah. So my system can still withstand that much perturbation in the gain until the closed loop system goes unstable. So that is why it is not just a measure of stability, but it is a measure of robust stability. So now, for example, you consider two different systems whose magnitude plots are like this, yeah, and whose phase plots are, say, for example, something like this, okay, and let us say this is where you have your gain crossover frequency, this is omega GCF, and this is where you have your phase crossover frequency, this is omega PCF, yeah. So this is basically then a measure of your gain margin. Of course, if you want to put it in the logarithmic scale in decibels, then this is 20 log of g j omega PCF, yeah, with a minus sign. Why minus sign? Because obviously if this omega GCF is less than 1, yeah, then this is going to be negative, so you put a negative. So you, because you want this quantity to be after all positive, so you are just taking the logarithm of this. This is the absolute, this is the gain margin in the absolute sense, and this is the gain margin in the decibel scale in the logarithmic sense. So that many dBs of gain margin you have, and you have suppose a second system on the other hand, which is, let us say, something like this, and this is, let us say, the 0 dB line. So this is the 0 dB line, and let us say you have a phase plot that goes like this. So suppose you have, this is your phase crossover frequency, this is omega PCF and this is omega GCF. So one measure of the stability is already there. You can see immediately that this is probably larger. So this is GM2, this is GM1. So GM2 larger than GM1 indicates that G2, the system, is more robustly stable, yeah, than G1. That is one. The other thing is, look at the relative spacing between omega GCF and omega PCF. The further apart omega GCF and omega PCF are, the more the margin you have for increasing the gain until they coincide, right. So in this sense, it makes sense to talk about this omega PCF and omega GCF as well as the gain margin, and of course I have not yet elaborated on this phase margin, so we will see that shortly. So this gain margin and phase margin actually do give us an indication about the relative stability, yeah, that is very, very, very important, okay. Now let us talk about the phase margin. What does the phase margin tell us? How does the in what way does the phase margin give us ideas about stability? Of course, we understand that if there is a gain term that enters, yeah, you might have if there is a Kp that is increased, then you have lesser and lesser gain margin. You are lifting the magnitude plot up, yeah, that way you are not only giving lesser gain margin at the phase crossover frequency, because the phase plot does not change with an increase in Kp, it is only the magnitude plot that gets lifted up, so you have lesser gain margin, and also you will see the other way, the gain crossover frequency moves more to the right, thereby coming closer to the phase crossover frequency. This is all well and good. What about the phase crossover frequency? In what way is it a measure of robustness, or rather what sort of perturbations could just affect the phase crossover frequency. Now recall, there are terms like e to the minus st, which we have not really studied in the Bode plot sense yet, yeah, because we only considered rational functions. But if you consider the e to the st, yeah, what is its magnitude plot going to be like? So you replace this with, so this is your g of s, say, then g of j omega is going to be e to the j omega t, right. In that case, what is the magnitude of this? The magnitude is nothing but 0 dB, constant. Yeah, this is cos omega t plus j sin omega t. So cos squared plus sin squared is 1. So it's 0 dB. But the phase plot of this, look, the phase plot is basically nothing but so phi of omega is equal to minus omega t. So it's a straight line. But remember, we have already made this a logarithmic scale. Yeah. So this is, let's say, 0.1, this is 1, this is 10, this is 100. So this is not evenly spaced. So in the linear scale, this would be a straight line, but in the logarithmic scale, yeah, so this is phi omega. So in the logarithmic scale, this will go very fast, yeah, because remember the amount of change that happens from going from 0.1 to 1 is much less than the amount of change that happens from going from 1 to 10. No, this is just a change of what? Just a change over 0.9, and this is a change over a range of 10. Yeah, so you can imagine that the amount of change that happens within this first decade, there is 10 times more change in this phase plot in the second decade, and 100 times more, and so on and so forth. So in the log scale, this phase plot would look something like this. So this is classically the example of a particular kind of a term, a time delay, which would do nothing but just perturb your phase plot. Yeah. So in some sense, you might perceive of this like just like this Kp, yeah, which is probably coming from the controller. So it's a desirable quantity. So the Kp is lifting the plot, but at the same time, this presence of this delay, which you might not have accounted for, which is something undesirable, the delay might actually perturb your phase plot. Yeah, so you might have a delay that gets added, and therefore your overall phase function, yeah, your overall phase crossover frequency shifts to the left. Yeah, so I've just given you an example. So a delay term will push omega PCF to the left, thereby bringing it closer to the omega GCF. Yeah. So this is the kind of perturbation, or this is the kind of undesirable component against which our phase margin protects us. If we have sufficient phase margin now, yeah, then just a small delay will probably not throw our system off. In the sense, it will not make our system closed loop unstable. Yeah, that is why this phase crossover frequency, this phase margin, which is basically the phase at the gain crossover frequency, yeah, that is important. What is that? So let me define it here. I have not probably defined it here. So how far you are away from this 180 degrees, yeah. So your phase margin is then defined as, so phi omega is your phase, yeah. So phase margin is defined as minus of minus 180 degrees, or rather, let me just, yeah. So this phase is obviously going to be some negative angle, no? So it's going to be basically 180 degrees minus phi, or rather 180 degree plus phi, but phi is of course going to be a negative angle here because of the convention we have adopted here. You can immediately see that the convention we have adopted here, this phi is going to be some negative angle. So how far you are from this 180 degree, yeah, at the point when the gain crossover happens, yeah. So that is the amount of phase lag that you can still tolerate. If someone gives you a phase lag more than that, so if you have introduced a time delay system, a time delay component which gives you a more phase lag than that, then you are in trouble. Now I am going to just try and wrap this up with our understanding of the Bode plot with the root locus and correlate them. So you see a lot of these deductions that you drew with this root locus can also be drawn with the Bode plot. So for example, if you have just 2 poles and maybe no 0 or maybe 1 0 here like this, yeah, you see that your system in this case behave like this in the root locus case. Yeah. Now, in case of the Bode plot, you will see that the magnitude plot will of course kind of tend to tee off like this, and then it will flatten out a bit, and so this is going to be minus 40 dB per decade because of the double pole, the complex pole pair, and this is going to be minus 20 dB per decade because the 0 sort of offsets that minus 40 to reduce it to minus 20. So, this is going to be your magnitude plot, and your phase plot is going to be starting here at 0. Yeah, then there is going to be a jump of 180. Yeah, and then there is going to be like a raise of, or rather I will be a little careful about this. So, it is going to be like this, come up here all the way here, then it is going to jump to minus 180. So, this is 0, this is minus 180, it will go up till here, and then it will jump up to 90 and continue like this. Yeah. So, your phase plot will be something like this. So, you see in this case your system actually never, yeah, it never goes to minus 180 degrees. So, omega PCF, yeah, tends to infinity. Yeah, even if you do not have this, 0 here, if you have this, you still know that this is how your root locus was, right. So, here in this case, let me draw this sketch here, it would be just this, and this, it would just start at 0 like this, and at the corner frequency it will be just this. So, only asymptotically it will reach 180 degrees like this. Yeah. So, this is going to be your actual phase plot. So, this is phi, this is 20 log m. Yeah. So, whether it is a second order system with a 0 or second order system without the zeros, you see from root locus you see that this closed loop pole never migrates to the right half plane, and I am claiming that by an understanding of phase margin and gain margin, if I just forget about this left half of this slide, this understanding of phase margin and gain margin will still allow me to infer the same thing about it. Yeah. How so? So, here is the point. You see omega PCF goes to infinity, that means there is no omega PCF as such, and at omega PCF tending to infinity, what does this fellow go to? This fellow is going all the way down. Yeah. So, if this is where probably somewhere here the 0 dB line is, at omega tending to infinity you have infinite gain margin. So, this is infinite gain margin, which translated into layperson's language would say that you can keep raising the gain to as high values as you like, you will never lose closed loop stability. That is infinite gain margin. What about phase margin? Yeah. So, for example, here you do have some finite phase margin here. In fact, that is something that is not very obvious to observe from this root locus. Root locus does not readily tell you about phase margin. So, that is why I said this frequency domain is beautiful, because it gives you not just the understanding that you had from this root locus in terms of gain margin. Yeah. You can see the same gain margin condition holds here also, because here also there is omega PCF tending to infinity. Yeah. Right. And so, therefore, here also you will see that infinite gain margin, which is consistent with our understanding based on the root locus. Yeah. So, we see that it is we have further in-depth understanding of the system stability. We can, in one plot we can see both phase margin and gain margin. Yeah. And phase margin is actually something that tells us something more, something that was not very apparent from this root locus. After all, root locus is not designed to talk about this phase margin. Okay. It is only the Bode plot which will give you information about both of these simultaneously. So, in some sense it gives you something more, it conveys some more information, and that is why we are fond of Bode plots. But, and here is where I will leave you with a little bit of discomfort about Bode plots. You see, this is all very well and good when you have nice systems, but let us not forget about the pathological case I had drawn a while back. Yeah, some root locus like this, where we figured that there were two crossovers, one taking it from the stable to the unstable region and the other taking it back from the unstable to the stable region. Now, you wonder what happens. Yeah, in such cases if you look at the Bode plot, so what I am saying is, so the Bode plot, and you can take this as an exercise, you can try this on MATLAB. So the Bode plot of such systems will have multiple crossover frequencies, and that is when things become rather messy. Later on, again I promise, when we do Nyquist we will have a better understanding of this as to which is which, but you see this will have multiple crossover frequencies. Why am I saying that? Recall, what was the condition for this root? You have to have at omega GCF the magnitude has to be 1, at omega PCF the phase is minus 180 degrees. So if omega PCF and omega GCF coincided, that is the definition of omega PCF and GCF, that at omega GCF it is 1 and at omega PCF it is minus 180 degrees. So at omega GCF and omega PCF coincide, you have 0 phase margin and 0 gain margin. So you are on the brink of instability. But now here you will have multiple such scenarios. First scenario, when you are going from the left half plane to the right half plane, that is one brink of stability and instability. The second scenario is when you have another value of omega at which you are going from unstable to stable back, and now you are like, all our understanding about positive gain margin and positive phase margin being the thing to desire goes out of the window. In general, unless you meet such rogue systems or some such typical system, we always go with the convention. But that is why I want to always put in a caveat, do not go by all these conventions all the time, use whatever you have, whatever understanding you have grasped about systems. In general, it is very true that a positive gain margin and a positive phase margin for an open loop stable system is desirable. But what if you already started with a gain such as this, which means that you had already taken your open loop stable system and increased its gain such that the closed loop system was becoming unstable, and then suddenly someone left the knob over there and you did not know this, unbeknownst to you it was left there, and then what you did was you said, okay, this is too high, so I cannot raise it to higher values, so let me try and reduce this. So you try to reduce the gain value and you keep going back here and it does not improve the performance much. Whereas let us say this person who tampered with the system, tinkered with the system before you, had increased the gain and left the closed loop pole here, at this place. So because you have at the back of your mind this notion that increasing gains is a bad thing, so you feel, okay, seems like the system is unstable, what do I do? Let me reduce the gain. You keep reducing gain and you keep reducing, go on and on and on, and you at this point when you have arrived, you feel, oh, this is still, probably this is not stabilizable at all. On the other hand, if you had been keeping your mind open to the possibility that such a situation has unfolded here, you might have just said, okay, let me try increasing the gain a bit more. So you increase the gain a bit more and voila, you are back in the stable region again. So that is why this root locus based understanding helps us in seeing why such a situation could arise. Now in the Bode plot scenario, if you just always fixate on this idea that positive gain margin is good, negative gain margin is bad, so basically I should always try to reduce the gain in order to stabilize the closed loop system, in this case it may not help you. So when you have such multiple crossover frequencies, then you need to be very careful. So in fact MATLAB has this command, if you just use gain margin, phase margin, you will just get one gain margin, phase margin, but there is a command in MATLAB specifically for such things. If I recall correctly, it is called all margin or all margins. Please check the syntax, okay. So if you give this open loop transfer function, if you type this command all margin or all margins for this system, you will see that MATLAB will spit out all possible phase crossover and gain crossover frequencies for you. And then you carefully look at the Bode plots and you carefully enumerate all those crossovers and check which is which, like which is going to correspond to like the crossover frequency where if you keep increasing the gain, it is going to make it stable or unstable. So how do you infer that from a Bode plot? You don't just blindly think it's going to be positive and negative, you just see that whether increasing the gain, if it's lifting the system up, then what's it going to do thereafter, right? So moving the plot which way, whether increasing the, so for example, let us say you have a Bode plot like this, and then something like this, and something like this, and like this, and like this. Okay. So let us say you have, this is the 0 dB line, yeah. So clearly there is one crossover here, there is one crossover here, and there is one crossover here, yeah. So let us say this is like your Bode plot. So then you are left to wonder as to what will happen, right. So obviously if you have to then look at the phase plot as well for this sort of a system, right. So if you look at the phase plot, for example, something like this, then something like this, then again something like this, probably, I don't know, yeah, something like this again. Okay, you can be a little cautious about this. Yeah, so this is this, then it goes like this, then again there is a rise, yeah, then again there's a further rise like this, yeah, and then again there's a flattening, and then again there's a fall like this, so on and so forth. You get the idea, right, and then you have this, yeah. So you see, you could have plus 180, you could have hit plus 180 degree on one direction, you could have hit minus 180 degree on the other direction. So you have to be very careful then, yeah, because remember the angle criteria is satisfied. The point I am trying to make is this: the angle criteria is satisfied for both plus 180 degree and minus 180 degree, and if you have such an ensemble, such a collection of pole and zeros, the phase plot, even if it hits plus 180 degree, even that is a concern for you, right. So the phase plot might have multiple crossovers, so you cannot just count on its crossovers with the minus 180, right, even the plus 180 is as bad, yeah. So you see here that this plus 180 degree, here you are almost maybe close to the plus 180 degree. So this is your most dangerous combination, it turns out, huh. Here you see you have your gain crossover, but you have sufficient phase margin out here, yeah. Here you have this gain crossover, but here you have also a phase crossover probably lurking very close by, because this is very close to 180 degree. Similarly here, this is another gain crossover, and you might have your phase crossover over here, yeah. So the phase crossover is to the right. So the phase crossover is to the right. So then you see, if you raise this too much, then this and this fellow will come closer together, and they will give you the imaginary axis closed loop pole, yeah. And on the other hand, if you raise this even ever so slightly, even before this can coincide, these two fellows, it seems, will already coincide, yeah. So you have to be very careful about which particular combination of phase crossover and gain crossover is the most dangerous, yeah. That will tell you the worst case scenario that you are dealing with, okay. So you might have this multiple crossover, multiple phase crossover, multiple gain crossover. So then you have to be very careful in dealing with these sort of things. So as I said, we will really not deal too much with the controller design in so far as Bode plots are concerned, but I will just give you a quick brief outline in a very sketchy way rather. I will not really talk much about the detailed numerical example or things like that, or show you on a Simulink window as I did with the root locus bit. So I will just give you a short, we will have a brief discussion on, let us say, the lag compensator design. Now typically we know that a lag compensator is introduced to address the steady state behavior, that is the steady state error, yeah. Now suppose you have a type 1 plant whose kV needs to be increased, okay. So suppose you have this kind of a plot like this. Sorry, this will not be a type 1. The type 1 will have something like this, yeah, 20 dB per decade, then something like this, and something like this, and then something like this, okay. So let us say this is a type 1 plant, and let us say its phase plot, it starts at minus 90 degrees because it is type 1. So, it goes all the way up until here excuse me, then it goes to 0 like this, yeah, then it again comes back to 90 here, and then it goes back to minus 180 here. Yeah. So, the typical type of sketch that we had drawn for our earlier example. Yeah. Okay. So, now apart from this, it is also desired to have a phase margin of say 60 degrees. Okay. So, you might wonder, well, lag compensators only help us in getting this steady state error reduced. How on earth is phase margin going to be improved? And after all, lag compensator contributes a negative lag, a negative phase, right. So, how is it going to improve the phase margin? It turns out that a lag compensator will actually allow you to do that. So, what is the typical structure of a lag compensator? A lag compensator will have S plus Z upon S plus P with some K possibly, yeah, and what you then have is, for this pole 0 relation, is that, remember that the P is less than Z, yeah, because this is after all an approximation of an integrator. An integrator has no 0, yeah, and a pole at the origin. So, here you just put the pole slightly off the origin and 0 again further way down. So, you have this sort of a location here, yeah. So, these are positive. So, basically if you recall, this is how we place the pole and 0 pair for the lag compensator, right. Okay. So, now what sort of a feature are we looking for then in the lag compensator? If we draw the magnitude plot of the lag compensator, the first corner frequency you will encounter is the pole. So, you will come across like this, then you will have this. So, typical lag compensators magnitude plot looks like this. What about its phase plot? Well, of course, it starts from 0, and then at this corner frequency it will go down to minus 90, and then it goes a little way off down this until it encounters the 0, and then it is again raised back. So, basically if I approximate this by a smoother curve, this is how a lag compensators, in fact we have drawn this earlier when we were considering this non-minimum phase system. So, after all, if anything, this lag compensator is increasing or decreasing the phase, no, it is taking it closer to 180 degrees. So, you might still wonder, like, how is this, what is this 60 degree phase margin business, how is it going to be achieved, right. But remember that a lag compensator also gives you this, right, this Z by P. So, it has the effect of kind of lifting, yeah. So, there are two ways I can improve phase margin. One, of course, I can add a phase lead, but of course, a lag compensator is unable to do that. But the other thing that it can do is, this lag compensator, it can actually lift, yeah, because the Z is greater than P, so it can actually lift, but it does so at the lower frequency range, right. At the lower frequency range, it sort of lifts this, right. So, let us do something here. Let me first apply a K here. Let me first choose a K here. So, if I choose this K suitably here for this lag compensator, then I will have modified this, yeah, then I will have changed this plot like this. So, this is with the K times the G plant, yeah. But now you see what I have then is, basically after lifting it up here, yeah, my gain crossover frequency has moved a bit to the right, and if my gain crossover frequency has moved a bit to the right, I better be careful, right, because as I go to the right, this is minus 180 degrees, I am getting closer and closer to minus 180 degrees. So, my phase margin is lower. But look, using this lag compensator, I cannot improve the phase. So, what am I going to do? The idea is then, I need a 60 degree phase margin. So, let me look at this plot here. Where on earth is this actually having a phase margin of 60 degrees? Yeah, where? So, let us check. This is 180 degrees. So, 180 minus 60. So, I will have to look for the place where its phase is, suppose minus 120 degrees. Yeah, and I keep a 10 degree more budget. Yeah, just because the lag is going to add some phase lag, right. So, let us say it is somewhere over here, I find that this is around 70 degrees. Yeah. So, my goal would be then that this green fellow, which is basically nothing but k times this plant, yeah, this green fellow is this k times this plant, yeah, this should have a gain crossover frequency at this point. So, can my lag compensator ensure that? You bet it can. What do? I basically design this zero end pole in such a way that I do not affect this high frequency asymptote, yeah, sorry, this low frequency asymptote, because this low frequency asymptote is actually going to help me meet my kV requirement. So, I have already used this k up, this k I have already used to lift this sufficiently. Yeah, remember, why is this going to help my kV improve? Because after all, the kV is nothing but this at omega is equal to 1, whatever is this, that is going to be my kV, no, this is going to be my 20 log of kV. So, if I increase this, if I lift this up, then basically I am improving kV, right. So, that is why I am going to increase k to a sufficiently high value till kV is met. Once I have met the kV, now I have to meet the phase margin requirement. If I have to meet the phase margin requirement, I better figure out, because my lag compensator is not going to help me with the phase. So, once I want that, then I have to figure out where I am getting a phase margin of not just 60 but a little more than 60, say 70 degrees. And now my goal is to design the pole and zero of the lag compensator in such a way that this is exactly where the crossover happens. How am I going to do that? So, let me just look at the characteristics of this. Yeah, this is the typical magnitude plot of a lag compensator. So, this lag compensator would have to be, the pole and zero pair have to be placed in such a way that, of course, this part, this is the 0 dB, say for example, this part should be not tampered with, this part should not tamper with this low frequency asymptote. So, this part should probably coincide with this. So, after this low frequency asymptote part has been dealt with, then, yeah, only then I start adding the pole, yeah, and then I add a 0. So, if I add a 0, yeah, sufficiently away here, then you see that this is going to contribute a negative magnitude, no, in the log scale. So, it is going to bring this down. So, what this lag compensator is going to do is, it is going to leave the low frequency part unaffected, it is going to bring down the high frequency part, and if it brings down the high frequency part, then it actually shifts the gain crossover to the left. Earlier the gain crossover was somewhere over here, now I have this gain crossover move to the left, and by moving the gain crossover to the left further, I have actually increased the phase margin. So, of course, I have said about all of this without any numerical values, and it might be a little hard to believe this, but I assure you that this works. If you want to convince yourself, take some typical example of the transfer function that we had considered the other day for sketching the Bode plot, and then try and do this design yourself using this principle, okay, and then test it out on MATLAB, and I am sure that you will find this convincing. So, with that we come to the end of our discussions on Bode plots. From the next lecture on, we shall start talking about a new topic, which is Nyquist criteria. Okay, thank you all.